Are you ready to get computer sciencey? We're talking about the RAFT algorithm where it allows the computers to talk to each other in a way that they can all agree together. There's a lot of computers out there and we have a lot of data and we need to be able to work together with that data to represent fault tolerance and reliability. When you're talking about the RAFT algorithm, you may have heard of other consensus algorithms as well, maybe CRDTs, the Paxos algorithm, some of those blockchains out there. These are all algorithms that are designed to help all these computers that are doing work or holding data or computing on something to gather all this data in a way that is consistent. So we need to have a consensus on how we're going to exchange this information and agree upon data. If we're looking at the RAFT algorithm today, which is a nice implementation that works pretty darn well to help distribute workloads across clusters, specifically more along the lines of data. We want to be able to all agree on the data that's being stored on each of these computers so that when I read data from one of those computers, I know that I'm going to get the same data as someone else reading the data as well that might be hitting a different computer. We need to have consistency and we also need to have reliability. This is what RAFT brings us. It's really powerful capability. Let's actually just walk through. What we're going to do is we're going to just walk through. I create a nice little Google Doc here that explains. Now here, let's just go to the top here. Reliable, replicated, redundant, and fault tolerant. I mean, we've got more R's in here. It should be RAFT, right? That's what I've heard. So this is essentially what RAFT stands for. Is essentially reliable, fault tolerant, which is what we're going for. An algorithm that is a consensus designed to manage a group of computers, and we're going to call those nodes, working together to keep a consistent copy of data. Imagine you have a group of nodes. RAFT helps make sure everyone agrees, even if some of the nodes miss part of the conversation or leave and rejoin later, which is really powerful because this happens all the time. Networks get disconnected, hardware fails, and we need to also scale up. We need to be able to add more hardware as needed or even reduce hardware. And RAFT allows you to do this. It allows you to keep that data in sync with all the other nodes in a pretty efficient and reliable way. At a trade-off of a few costs, we'll probably be talking about that as well. There are multiple aspects to the RAFT algorithm that help all these nodes stay in consensus about what data is available to be read from clients connecting to those servers. Just take a look at how sort of we're gonna dive through. We're gonna walk through various aspects of the RAFT algorithm. It does kind of two things really, really well. One is keeping its own system in check, being able to understand the health of the cluster. And this is done kind of transparent to anyone who's implementing the library. If you're importing a library from HashiCorp, for example, the library will take care of sort of managing the node's state and communicating with the nodes. So that way we know who's the leader, who's the follower, and if we get into a scenario where the leader goes away, how do we then come up with a consensus to then re-elect a new leader in the group? So let's just do some walkthroughs. We're going to walk through some diagrams. This is what we're going to do. We're going to walk through some diagrams. We look some pretty animations. We'll talk about those. First, let's start out with this algorithm right here. So starting on the left side, we're going to move over to the right. We start up a node boots up. The node is now a follower. All the nodes start as a follower. And then we start an election. So it looks like here we've booted up the entire cluster. Okay, so everyone immediately starts out as a follower. So this is how we're reading the flowchart. The entire cluster starts up. Say there's like, in this example, we have 5 nodes, let's say. All right, so we have 5 nodes. They all boot up. They all start as followers. Then they are all candidates, depending on a timeout. They don't upgrade themselves to a candidate until a timeout. Now, if we're looking at this animation here, see how there's this little semicircle outline that's sort of shrinking and rotating counterclockwise? This is the timeout. This is the time before it will consider itself a candidate. This is necessary as part of the consensus algorithm, so that way not everyone appears to be a candidate at once. This allows the cluster to then elect essentially the fastest one to be considered a candidate. The first person to candidacy will get voted the leader and they will win, typically. There are fail scenarios where it can get bad. The good news is this works pretty much most of the time, so we don't have to worry about those other edge cases. So then once we elect ourselves a candidate, we time out and a new election begins. It receives votes from the other majority of the servers, and then it becomes the leader. Discovers the server with higher term. What? Discovers the current leader or new term. So what is this term? I need to look at this really quick. Hold on. What is the new term? I need to look this up. Hold on. I found it. I found the terms. All right. So we've got terms. They're essentially different parts of the election in the emergence of a leader. And in some scenarios, you can have agreement or disagreements. And so this is sort of just time phases is what we're doing. We're going through time. We're moving forward. Election, normal operations, leaders not emerging or emerging. And then we have the fourth term, and in this case, it's the steady state. Hey, we're in a good position. Everyone is happy. The cluster is happy. We have a leader. We have all our followers. There's no more candidates, and we are in good standing. This is the workflow of how that operates. So that's pretty straightforward. Let's look at this animation diagram really quick. You can see that all these dots they're essentially votes or casting votes saying, hey, so it looks like S3 is the first to see, so it's timeout first, boom. And then it says, hey, I'm a candidate. All the other nodes say back, ping back with that green dot. So like first, I'm a candidate. All the nodes go, oh, okay, like we acknowledge your candidate. It's like, I want to be leader. Okay, we accept you as a leader. And the vote is over. And now we have the leader that has been elected. This only happens because S3 was faster than all the others. That is the leader election process. And that works really well. I'll tell you where it doesn't work well, though, is when these nodes are distributed globally across multiple data centers. And they all have various latency differences. So even if you randomize the timer, it's possible that there's overlapping. And then candidacy votes can be cast for multiple regions simultaneously. And then you'll have a battle because multiple people think they're first, but they're not. And then you'll have multiple leaders, and that will be a bad state, and that can totally happen. So this is a problem that we faced at PubNub. We're a globally distributed network where we connect devices to the closest region. We run across all of Amazon's availability zones. And so when we've used the RAFT algorithm in the past, we've been in a scenario where a leader can fail, candidates pop up across the world, and they can't vote themselves into a position of leader, and then you get essentially downtime that cannot be resolved by the algorithm itself. It's not self-resolvable, even though there's plenty of hardware for it. So as humans, we have to go in and reboot the system in a sense. So there are problems with the RAFT algorithm when you are not all sharing the same performance. So that's really critical. You kind of want to keep this maintained in a single data center region. This is really good advice if you are dealing with multiple regions simultaneously. All right, now we're going to walk through the components of RAFT, the system that lets us stay in consensus across multiple nodes or servers or computers. So we have a bunch of servers and computers. We need to make sure that the data is consistent across all those nodes. And we use RAFT for this. It's actually pretty simple from conceptual perspective to understand what's going on here. We're going to walk through it. We're going to walk through the components of RAFT. And then we've got this really fun kitty cat diagram that walks us through parts of the phases. So let's start out here. So we've got every node can be any of these states, essentially. Every node can be one of these things. There actually can be multiple of these things. But let's walk through the best possible scenario. The happy path. Let's walk through the happy path. You can have the leader. The leader is the main coordinator who makes decisions and tells everyone else what to do. Okay, now from a business perspective, this is a kind of system that is not... I'm like, uh-oh, we've got a problem. We've got a bottleneck of a leader. Someone who's critical to the system has to be alive, and it's not... It's a problem because if that leader fails or is unable to communicate with the other nodes, then we've got latency in the system, essentially. The leader is a coordinator that coordinates everything else in the system, mostly for writing data. reads, if you're reading data, can actually come from any of the other nodes, including the leader. So this is where the RAFT algorithm shines, and it's wonderful. If you have a high read concurrency, then you're going to be pretty much fine under the majority of the cases, and you can tolerate some write latency under failure scenarios and some typical write latency during the consensus algorithm to a consistency factor. You can have a write consistency factor of 100% where you require all the nodes to acknowledge that they've received the commit log. And if they have, then you can sort of send the thumbs up to all the other nodes to say, okay, now that everyone's received it, commit your data, and now everyone will nearly simultaneously have all the same data. So there is still a teensy bit of eventual consistency in there. There's just a little bit, tiny bit of eventual consistency when the leader tells all the followers, the new data that you wrote just now, it is good for you to serve to new clients that are connecting. So there's just that short window. And we're talking milliseconds, even sub-milliseconds in cases. So it's a very short window. Okay, so we've talked about the leader, and there's followers, which is everyone else. It's the entire group. The group of members who listen to the leader and follow its instructions. I mean, that's actually why it's really simple to understand, is essentially, you essentially have these two roles in the system running consistently. This is the roles that occur. So you've got one leader and a whole bunch of followers. The followers can all service read requests. So anytime a client that's connecting into the cluster needs to read data, any of the followers can service that request. The leader can too as well, but the leader is the only one that can really coordinate a write amongst the systems. Now, the third component, or a third state of a node, is a candidate. This happens when there is no leader. A candidate will elect itself a candidate leader based on a random timeout interval. The first one to hit that random timeout interval when there's no leader will essentially elect itself as a candidate and broadcast its candidacy to all the other nodes. And in that case, it typically wins and it becomes the new leader. So this only happens under fail scenarios, and it also happens during cluster boot. So you have got a brand new cluster, and all the nodes spin up, and then they can all communicate with each other to become the leader, and that's how that works. So those are the three states, the three components. A node can be a leader, it can be a follower, and it can be a candidate under just a couple short scenarios, right? Cluster boot, and when the leader fails. How does RAFT work? It's a consensus algorithm that connects all the computers together to coordinate data consistency, so that way you can have a strong consistency when servicing clients that need to read data or write data. And we're going to look at the fun kitty cat diagram from Denise21 and MT165 that did this night. There's two parts to it. It looks like a lot's going on here. There's a lot of words going on here. So the RAFT consensus algorithm is all about coordinating computers or servers in a way that allows them to all have the same data represented. And if some of the nodes fail to get the right data, then they can catch up in essence. They can correct themselves. That's the whole point of the RAFT algorithm. Let's walk through this diagram. We'll start here at the top. Let's start at the very top. So RAFT is a consensus algorithm. It is a process for getting multiple machines to agree. And a machine is a node or a computer or a server, where you've got a physical hardware rack, 1U, 2U, 4U. Well, do we have 4? Yeah, we still have 4Us, don't we? We need a lot of big giant GPUs and ASICs. So we have these servers that are running. It could even be your computer can be a node. Your laptop, your phone, these can count as nodes. They totally can. You might not want to run RAFT on them because usually a cell phone and a laptop and someone else's cell phone and laptop might be in a different network. Latencies are going to be crazy. And the RAFT algorithm has some issues with inconsistent latency. So what you need to have certainty of is that all the nodes are generally electable as the leaders with identical capability. So that's something that is sort of dependent on RAFT. And it still can work in inconsistent environments. You can just run into scenarios where humans have to get involved. I've experienced it firsthand. All right, so it's a process for getting multiple machines to agree. Raft, which kind of looks, I guess we're going down a river, which makes sense. Look, we've got a raft, and then we're going down the river of the kitties and telling the story. It totally makes sense. Raft doesn't stand for anything. It says it doesn't stand for anything, but it looks like an acronym, doesn't it? And I'm pretty sure we were looking at it here. It said reliable, replicated, redundant, fault tolerant. So we could acronymize it if we wanted to. We totally could. And let's see, it's a bunch of logs tied together. Oh, that is clever. Oh, I really like that. Okay, so there's a replicated log. So whenever data is written, this is a transaction essentially, or it's a log. It says, hey, we need to write this data. That is broadcast to all the followers via the leader, and this gets appended to the follower's log. And then as soon as the log is appended, the followers will emit an event saying, hey, I've appended this to my log, and I'm ready to commit it. And they broadcast that back to the leader. The leader waits for all the followers up to a write consistency level of, say, 50%, to then acknowledge that they've received the log, and the leader node will then broadcast commit, put it on disk, and save it permanently, and make it available to anyone who's reading the data. It'll broadcast that back, and then that new data is then counted as written. This is heavy-handed, but it does allow a level of consistency that is very valuable. That's why I like this clever algorithm. It's like, okay, so we're going to be on a raft, and the raft itself has a bunch of logs, and the logs are tied together. I get it. It totally makes sense. This diagram of kitty cats makes it a lot more clear. Okay, why do we want to do this? Before we jump into the why, what uses RAFT? There's actually several systems in production today, including PubNub. We use RAFT for two major systems. We have so it's used in many projects in the real world, including does it say excluding or including? Well, etcd, Consul from HashiCorp, Nomad from HashiCorp, and those are systems that we do use at PubNub today that help us coordinate workloads across various systems. Consul is used as typically a KB system that is used to help coordinate configuration across clusters. And in order for us to get around the RAFT problem of cross-region connectivity for leader elections and commit latencies, we set up dedicated Consul clusters in every single Amazon availability zone. There's a lot of Amazon availability zones. So we set them up in every single one. And so each of these clusters are essentially independent, and they're all sort of isolated to each zone. And then we have another RAFT layer on top of that, which luckily Consul has added as sort of like a global layer, which is a second layer of consensus. Still using RAFT, but the timeouts are much higher, much larger. And it still allows you to copy commits across regions. So you have a global consensus across all of your clusters. So there are a lot of systems that use RAFT. We use RAFT, and we just need to make sure that we're cautious of how RAFT has some limitations. Any part of a distributed system can fail, and this is why. So we're jumping into the why now. So anything can fail. Hardware fails all the time. Networks get unplugged. Latencies are introduced. Problems can happen. Consensus across several nodes gives us backups of data. Yeah, so we need to be able to copy data across multiple nodes, so that way when things fail, and they do, you still have a service, an API provider like PubNub, who has all the data available across all the nodes globally in all of the Amazon zones. So that data is available and made still accessible even during hardware failures. You will never notice, because there's enough data being copied in a consistent fashion that allows for this. And so that's why consensus algorithms are really valuable. And one of those failures can be a network partition, which isn't necessarily a failure. It's just splitting of networks for scalability purposes. What about network partitions? Okay, let's read through it. In a partition, if the leader falls on the smaller side of the partition, a new leader is elected within the majority side when the partition ends. Messages received by the minority side are discarded, and those nodes converge on the state to match the majorities. So in the case where you've got multiple leaders and an uneven split of nodes as they've lost connectivity with each other, you will have still the opportunity to I guess in this case, if you've got multiple leaders, it has a system built in to detect, oh, there's more than one leader, we need to have a new election. And so this will happen. The details are not clear about that. All I can tell you is it has failed us in the past for those types of scenarios. So there are some things to consider. You want to make sure to have an odd number of nodes, and as best you can, have enough nodes so that way enough of the partitions can still operate successfully if needed. And if some of the nodes fail in this case, you can still have data that's being read to from followers. So you can still have you can still service reads, but writes might have some latency in that case. All right, let's go down the river. Let's go down the river here with the raft and the logs. This is actually going to be pretty simple. This is all about just one write. We're going to do one write. We're going to write a user's name. Well, the name will be cat or something, right? Well, a cat named Denise, for example. So we want to write that data to a KV store of some sort. So we're the raft, we're the log, we're going down the river. Now we're going down the river. When a new write happens, any node can accept a write. So a request to write data, any of these nodes can accept a write. The message is then forwarded to the leader node. This is where the bottleneck comes in, of course. Write-heavy applications will have a challenge because you're bottlenecked at the leader. So all writes are forwarded to the leader, and the leader queues the message. Copy me. Ack. Okay, so we're having an agreement here about data being written, while the followers copy it to their logs. So what happens here is it's less clear that the leader will broadcast the log or the write to all the other followers. So the message, a write comes in, the follower node accepts it, forwards it to the leader broadcasts it to all the followers and saying write. Everyone acts back and forth, and then when a quorum have copied the message to the leader, commit the new data and will now return on read. That's describing this ack process. So all the nodes have received the write command. Those followers ack up to the leader, and the leader sees, okay, 50% of you have already said you received the write log. The leader will then say broadcast commit to everyone, and then the commit message will lock that change in, and going forward, anyone who reads data will receive that new information. RAFT, the consensus algorithm, brings with it quite a few different capabilities that are intended to coordinate lots of servers and nodes so that they can have a level of consistency when we're writing data. And there are various aspects to how it works. There's leader election and log replication, committing, a whole bunch of things. We'll walk through. So I've got a list here. What we're going to do is we're going to walk through this list. I'll read all the different pieces and give sort of thoughts and ideas about it, how it works. So leader election. Now we're starting at the very beginning. This is saying we have one node or a bunch of nodes, and they all just come online, and now we're going to start the process. So when you start, nobody is a leader. We spun up a cluster. We have one node or 10 nodes. We all start as followers. Each of the nodes can announce they want to be the leader, though only one at a time essentially will, and that's based on a random timeout when one of those servers elects to be a candidate. The nodes vote, and the one with the most votes becomes the leader. That makes sense to me. Seems like a fair... This sounds familiar. I think I've heard about this before. If there is a tie, or if nobody gets enough votes, the voting process restarts. And this can keep happening until someone is eventually the leader. Pretty straightforward. Okay. There can be scenarios where you have leader lock. I've seen it, and it's been a problem before. And when this happens, 100% of the cluster can no longer receive write data, which is a problem. And this is a pretty decent problem that can occur. And you can also have a perceived leader lock if the voting process continuously just results in a tie over and over and over. And it can eventually get to a leader election. It's just going to take a while. And I've seen it, and it's terrible. So beware. Good news is, in 2024, a lot of those problems have been mitigated with just tuning and better approaches. So those situations are rare these days. Log replication. So once a leader is chosen, it starts telling the other nodes what to do. So it makes sense, a leader and follower algorithm. It sends them logs or instructions. For example, a leader says, add 5 to our total score. All the followers will do exactly that. The leader keeps track of these instructions in a log, and each follower keeps its own copy of the log. So this is the log replication. The leader broadcasts the log to all the followers. And then we get to the next phase, the commitment. When the leader sends instructions, it waits until most of the followers say, I got it. I received your instruction. You told me to add 5. So I'm going to do that. Before I do it, though, I'm going to tell you that I received your instruction. Once the leader hears back from the majority of the followers, it tells everyone to mark the instructions as committed. It's done. So then it broadcasts back the ID of the log and says, commit this. All the followers see that. They will lock that change in place, and now anyone who reads the key for that data point will receive the new committed data. This ensures that even if some of the nodes didn't hear instructions initially, they will eventually catch up. So there is some eventually consistency here, some eventual consistency. The idea is to sort of minimize that eventual consistency to make it strong. And you can make it very, very, very strong to say, wait, do not commit this right until 100% of the followers acknowledge. That's dangerous, because if any of the followers fail, or they go offline, or they're having issues, then the new data written will not be committed until the entire cluster says, okay, that node is gone and it's just gone, in which case it can remove it from its inventory and then send out the commit message to the remaining followers, or it eventually catches up. So that can introduce a lot of latency. So it's dangerous. Your write consistency should be, a majority is fair, right? So 60-ish%, 50% is fine. All right, now we've got fail scenarios. If the leader goes offline or doesn't respond for a while, the nodes will start the election process again to choose a new leader. Any candidate that wants to become the new leader has to gather votes from the majority of the nodes. This all happens through a randomized timeout. So essentially the first candidate, or the first follower in this case, as soon as its timeout ticks to 0, it'll say, I'm a candidate, and it broadcasts that to all the followers. All the followers will typically acknowledge that is a candidate, and then they will vote back and forth and acknowledging that candidate as a leader. So it's usually the first one to elect candidacy will win, and that's kind of how that works. So RAFT has some promise of safety and consistency here. RAFT ensures that as long as most of the nodes are following the rules, the group will always come to the same decisions. Well, hold on a second. So that means that some of the nodes can choose not to follow the rules. You're going to have some misbehaving nodes, and you might not know it. They could look like they're following the rules, but say they can make some changes on their own. You can have some rogue followers. You really could. This could happen. I mean, obviously, it's not going to in the real world unless someone is, they're having fun. Though it is possible to trick the RAFT system into thinking that all the followers are, they're honest. But you can have some dishonest followers, and they can do anything they want, and there's nothing you can do about it. The RAFT algorithm does not have any special considerations. So this is like where the idea of like blockchain comes in, where you have the ability to enforce these followers, and they have to follow the rules because there is a chain of signatures that validate consistency. So in this case, the RAFT algorithm, as far as I can tell, allows any bad actors if you wanted. So this is why you probably wouldn't see RAFT being used for a blockchain consistency algorithm. You need to have a cryptographically signed series of events that allow everyone to agree on the same thing in a distributed system without a leader scenario. which I prefer in terms of general architecture. I like not having a single point of failure. Just my opinion. It's a fair opinion, right? I don't want a bottleneck that's one of the nodes can fail, and then it introduces latency in the system as it has to bring up a new leader. It actually works really well. We actually use it at PubNub a lot. We use the RAFT algorithm today, and it does good for certain use cases. So we do use it inventory management and KB stores and things like that to coordinate data between some of our pods in our Kubernetes clusters. So even if some of the nodes get disconnected, later on they can catch up with the logs and get updated. Yes, okay. So this is where RAFT comes in, and it's actually kind of nice with that log. They can, one of the nodes, it is heavy-handed, will incrementally receive older and older data and ask from the leader gradually, hey, I don't have this commit. Can you send me the data leader? And the leader will send it over. Hey, I don't have this one. Hey, I don't have this one. And it's also possible there's a snapshot involved where if a new node that has no data can then capture a snapshot of the data and then catch up just on a series of logs that haven't been committed to the snapshot. So that helps bring on new nodes more quickly, rather than having to one by one collect all the updates and read writes, deletes, all those things. And so that's the gist pretty much of RAFT. It coordinates groups of computers to agree on data and staying consistent. Even when some of those face issues, some of the nodes they can fail, they can disappear and they can come back and they'll be out of date and they need to be able to catch up. It does this by electing a leader and having the leader tell all the others what to do, all the followers, and making sure that everyone stays in sync by keeping logs of instructions. It keeps track of it in a book, like a spreadsheet, essentially. If the leader fails, everyone votes to elect a new leader, ensuring that the group keeps working smoothly. And that's RAFT, and it does a good job. We've been using it for a decade and a half now, and it's actually pretty good as long as you operate it in a way that mitigates some of the edge cases for self-healing. This is the self-healing segment down here at the bottom. If the leader fails, everyone votes to elect a new leader. And in most cases, especially in 2024, it works really well. And so we like RAFT, and RAFT is a pretty darn good consensus algorithm. Philip O'Toole is the author of RequelLite. I've been calling it RQLite, but it makes sense, like SQLite or SQLite, or you can call it RequelLite. Philip says it's RequelLite. Watching Philip's YouTube video on distributed systems with RAFT has shown that Philip has built many distributed systems and has leveraged the RAFT algorithm for these distributed systems. What's great about it is it's actually a pretty straightforward algorithm, especially when you're using a framework, and the one provided by HashiCorp. They have a really good implementation in Go, so that now you can add distributed-based RAFT consensus among a distribution of computers and servers, and they make it easy. It's a nice framework. It really is. Philip O'Toole's YouTube video is here that describes at GopherCon how that works, and even with some Go code to say, here's how you implement it to have your own distributed system, and it can be for anything. You can have a dedicated in-memory KV store, essentially replicating what Redis does, or Memcached. You can have a disk-back system like SQLite or any other kind of database system, and then you can use RAFT to transmit all the change logs to all the other nodes, so that way they all stay in sync. And so this allows you to create a really good, high consistency and excellent easy to scale high read scenarios. So if you've got, here's where RAFT is really, really good. Like it's phenomenal. When you have a lot of readers, your concurrency for high read is very high. Very high read concurrency. It is a little more challenging to scale the write consistency. So if you have a ton of writers and a high concurrency on writes, then RAFT is going to struggle a little bit, because right here, the leader is the one responsible for coordinating all the writes. This is a single point of failure and also a bottleneck in general. you can add into Raft a layer of sharding. You absolutely can. And so you might have multiple shards. So that way you split the data and then you just have multiple Raft clusters. That actually totally works fine. You can do that. And that allows you to increase your write concurrency. So you can scale pretty much infinitely if you use that approach from a write concurrency perspective. And a read concurrency as well. If you have high reads, it's pretty easy to do that. You just add more nodes and it does a pretty good job. Philip O'Toole sort of describes here the HashiCorp RAFT programming interface with the Go programming language. And look how simple it is. Philip did a really good job describing how to encapsulate a KV operation using the HashiCorp RAFT algorithm. And it was fantastic. It was a great video. And look, there's only a few functions here that you have to be aware of. An apply for applying all the committed entries in the node's KV instance. A snapshot returns a snapshot of the node. So the RAFT algorithm will ask some of the followers or maybe the leader to create a snapshot. And then that snapshot is going to be a complete picture of all the data. And then you can take that snapshot, save that snapshot probably on disk, and then you will resume from there additional logs or change logs, right? So you have a change log that continues from there. And then the snapshot happens, and then you can collapse that change log, you can discard it, and then save the snapshot, and then continue on down. That's pretty cool. I really like that. Write snapshot to persistent storage. All right, so then you've got a persist function where you need to implement that. A restore function, so say a node has a failure or it needs to come back online, or a brand new node comes in, it needs to be able to resync. And then snapshot release. In Philip's videos, this is a no-op is what Philip described. And in this case, I don't know what it does. It seems to be never really needed, as probably when the snapshot is complete. I'm guessing here in that case. Philip also walks us through the RAFT-based KV store implementation with the conceptual view. You have a client, which is going to be a phone, a web browser, or your laptop, is going to either write data or read data. And the way Philip describes it is a really good implementation that allows any of the followers to also act as a leader. When a write comes in, the follower will automatically route the write to the leader node. That's important. You definitely need that because it helps the client implementation a little bit easier. The client doesn't have to worry about selecting the right node when it needs to write data to the cluster. The client can just get any of the IP addresses, maybe through a DNS round robin. It can get a whole bunch of IP addresses, and then it can just choose to connect to one of those nodes. And then it can send all of its read and write commands to that node. And that node, which implements RAFT, will be able to facilitate any kind of request. I like that. That's really smart. That's excellent. What RAFT solves, I like this slide here that Philip provided. It solves concurrent updates, which is great. So only the leader can make changes. That means you can have multiple writes coming in, and the leader will queue up all of those write changes and then dequeue them as it commits those logs, as it broadcasts the changes up to all of the followers. So consistency is key here. RAFT log is what drives the whole thing for the consensus, right? We get the consistency. And this bullet here, this is a fair statement. This really is a no eventual consistent result. This means that essentially whenever you make a read, no matter who's reading from what node, all the nodes will have the same data. That's the whole idea. And that's what RAFT solves. Now there is some room to have some eventual consistency because the acknowledgement from the follower nodes has a write consistency value of 50%, or a majority could be 60%, where in that case the leader node will broadcast to all the followers to commit its change. And it's possible that a few of the nodes might be just a little bit behind. Even if they still would have received the commit message from the leader. And in that case, for the most part, within maybe less than a millisecond, everyone will eventually be consistent in that time frame, which is a very small window, very, 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 very tiny. Enough time to really consider the system in this case as not eventually consistent, is like strong consistency. That's key. That strong consistency. Fault tolerant, yes. Only a quorum needs to agree. Failure detection via heart beating and leader election. That's how the RAFT system works. It all happens through leader election, and the leader drives the followers and provides all the instructions. So that way, everyone is in lockstep, essentially, and they all provide the right data as close as possible to having a fully consistent cluster that's ready to scale, basically boundless on the number of reads. It does really good with that. And then if you need to have a high number of writes, you can potentially tune down the write consistency. So instead of having 50% of the cluster acknowledge, you can just say 10% or 25%. So you reduce that write consistency requirement. Though you still have an upper bound, so you can have multiple clusters through sharding, and that would allow you to still keep RAFT going, and then you would be able to shard your data. This is also needed because you don't want to have like super giant disks either if you have a large amount of data. So you could shard the data so that way you can split the data across lots of disks and also provide higher read concurrency and higher write concurrency is what I mean specifically. HashiCorp has given us open source MIT license access to the RAFT consensus algorithm. It is amazing that they've done this. It's implemented in Go. We actually use this algorithm at PubNub to coordinate some clusters of nodes within our system, and we use it to help coordinate some of our PubSub services via a KV store, via Consul. Consul is a HashiCorp tool that allows you to store data that multiple nodes can access, and also send triggered signals to receive change notification events. So say, for example, a new pod comes online. That pod will register its IP address, and that IP address could be committed into Consul, and via the RAFT consensus algorithm can then write across a cluster, a RAFT cluster, in this case a Consul cluster, will commit that data and then broadcast the change events. And that allows us to have essentially inventory management capabilities. And we use Consul for this. We might be moving away from that. When we migrated to Kubernetes, we had the need to have global distribution. And so we had to make some considerations. At the time, Kubernetes didn't have a way to join together regions through a collected KV store that allows us to coordinate pods across multiple regions, because we deploy our code to all of Amazon's availability zones across all of their regions. So your device connects to the closest data center, and we'll be able to use the PubNub APIs at the closest data center and then communicate with all the other nodes around the planet. And so that's what we use our RAFT that's what we use RAFT for. And Go does is what HashiCorp chose to write their RAFT library in, and it does a really good job. So RAFT is a Go library, in this case that HashiCorp wrote, that manages replicated logs and can be used with an FSM to manage replicated state machines. It is a library for providing consensus, and in computer science, consensus just means agreement. Right? It's a way. It's an algorithm on paper, a series of steps that all the computers will adhere to. It's like rules. It's a whole bunch of rules, and the computers just follow those rules. And it is a set of rules that help coordinate multiple machines. There's a lot of use cases for such a library. They're far-reaching, as what they're saying, such as replicated state machines, which are a key component of many distributed systems. They enable building consistent partition-tolerant systems with limited fault tolerance as well. So, I mean, obviously you can't have infinite fault tolerance, because you could lose all everything can be turned off with a switch, and you can't really recover from it's gone at that point. If you turn off every server simultaneously, you can't you can only be so fault tolerant. So it's pretty straightforward to build using Go. above. We're actually what is it? Go 1.23 ish or 120. There's a lot of Go versions beyond this. So we can read the Go docs, which tells you how to implement the RAFT algorithm in Go, so that way you can use the RAFT algorithm with whatever project you're currently needing it for. And they provide a nice little protocol description here. RAFT nodes are always one of the 3 states. So you've got a node, you've got 5 nodes, and each of these nodes will be in one of the following states: a follower, a candidate, or a leader. All the nodes initially start out as followers, so everyone's a follower at the very beginning. In the state, the nodes can accept log entries from a leader and cast votes. If no entries are received for some time, nodes self-promote themselves to candidate state. So if they didn't hear from a leader, either through a heartbeat or a commit to write data of some kind, they will, after a set timeout, elect themselves as a candidate to become a new leader, because the leader stopped talking, so the leader went away. In the case where the candidate states, nodes are request votes from their peers. So that means that the candidate broadcasts its state to all the other followers, saying, I'm a candidate to be the new leader because we haven't heard from our leader for a while. The peers will be able to receive and cast their votes, and the candidate itself receives a quorum of votes, then it's promoted to the leader. So then everyone will be able to say, okay, now you're our new leader. The leader must accept the new log entries and replicate all of them to all the followers. In addition, if stale reads are not acceptable, all queries must also be performed on the leader. Interesting. If stale reads are not acceptable, all queries. So you can, this is interesting. So this is directly here in HashiCorp's RAFT implementation of Go, which we've been using a lot. This last sentence is interesting because I thought there was a more strong consistency of data across nodes. And in that case, you can maintain that as long as you use the leader as the reader. So say your cluster is far behind and it might be trying to catch up due to some failure scenario. You can increase your consistency to 100% by just making sure all the reads hit the leader node. That makes sense, though that's a bottleneck. That seems like a problem. Once a cluster has a leader, it is able to accept new log entries. A client can request that a leader append a new log entry, which is an opaque binary blob to RAFT. RAFT doesn't care what it is. It could be anything. It's just some chunk of data. The leader then writes the entry to a durable storage and attempts to replicate to a quorum of followers. Once the log entry is considered committed, it can be applied to the finite state machine. Just in case you were wondering, earlier on we had an acronym in here that was described here at the beginning. FSM, finite state machine. All right, so we have an obvious question that relates to the unbounded nature of a replicated log. RAFT provides mechanisms by which the current system can be snapshotted and the log is compacted, or I guess in that case, deleted. You might keep like some backups of logs, though once you've snapshot, you don't need the log anymore. Because the finite state machine abstraction, restoring the state of the FSM must result in the same state as the replay of the old logs. This allows RAFT to capture the finite state machine state at a point in time and then remove all the logs, where you get to delete the logs, right? You get to truncate the logs that were used to reach that state. This is performed automatically without the user's intervention and prevents unbounded disk usage, as well as minimizing time spent replaying logs. Yeah, that makes sense. So say, for example, you've got one key and you're writing to that key a whole bunch over and over and over and over, and that key is constantly being updated. If you're doing this in a regular database fashion, you're not taking up too much disk. You're just overwriting that entry multiple times. Since there is a log that's being kept with the RAFT system, it's always appending. So even though you're writing to the same key, the value is constantly growing. So you can have an unbounded log, which is a problem because you'll run out of disk. So that's what snapshots take care of here. Lastly, there is an issue updating the peer set when new servers are joining or existing servers are leaving. As long as a quorum of nodes is available, this is not an issue, as RAFT provides a mechanism to dynamically update the peer set. If a quorum of nodes is unavailable, then this becomes very challenging. Yeah, seen this before. You got some problems. For example, suppose there are only 2 peers, A and B. The quorum size is also 2, meaning that both nodes must agree and commit on the log entry. If either A or B fails, it is no longer possible to reach a quorum. Danger zone! The cluster is offline, even though there are servers running. You have a fail scenario. This means the cluster is unable to add or remove a node or commit any additional log entries. This results in unavailability. Yeah, it's gone. It doesn't work. The consistent algorithm for RAFT, it requires that you have enough nodes that are active and available. At this point, manual intervention would be required to remove either A or B and restart the entire thing. Yep, we had to do that multiple times. It can get pretty bad. So the minimum RAFT cluster size is a node of 3, and you can only tolerate a single failure in that case. So you want more than 3 nodes. And this is what we've done. We've done quite a bit. We want to make sure. So while a cluster of 5 can tolerate 2 node failures, the recommended configuration in that case obviously is going to be, 5. You should do 5. Don't do 3. This maximizes availability without greatly significantly impacting the performance. That's right, yeah. And you notice that they didn't really go above 5 because it can start slowing down because it's a bottleneck to the leader as the broadcaster for all the writes. So you can start getting a slower and slower system if you go too big on the number of nodes. In terms of performance, RAFT is comparable to Paxos. Assuming stable leadership, committing a log entry requires a single round trip to half of the cluster. Thus, performance is bound by disk I/O and network latency. Paxos is another consensus algorithm that is a little more complex, but basically achieves the same thing as RAFT. Talking about consensus in computer science, it's an algorithm that has to deal with distributing logic across computers. How do computers communicate with each other in a way that they all can agree upon when they exchange data? There's a cap theorem that specifies there is only a specific pattern that is available to you when you're creating a distributed system. You can only have 2 of the 3. There's a limit to the system on how they can communicate in a consensus algorithm. Let's walk through the cap theorem. The cap theorem in computer science is a theorem, or Brewer's theorem is a computer science principle that states that a distributed system can only provide 2 of 3 guarantees at the same time. What are those 3 guarantees? Consistency, availability, and partition tolerance. What are all those things? All right, so consistency says that all the nodes can guarantee that they all have the same data. When someone makes a request to read data from that node, all the nodes will have the same data. That's consistency. Availability says that you can have a lot of uptime, but there might not be a consistent data availability. So some of the nodes might be out of sync. You're trading that off to make sure that you have enough systems online and available still to be able to serve data, even if it's stale. That's okay. And partition tolerance is in a scenario where part of your cluster becomes unavailable. However, even under that scenario, your overall service in the cluster can continue to operate even if there's a failure in part of that cluster due to partitions or outages or any other scenarios. So a distributed system is a network that stores data on multiple nodes, such as physical or virtual machines. And we've got this pretty diagram here, and it even includes like some examples. So we've got consistency. All clients see the same data at the same time. That means that's a really easy to one. That's really easy to understand. I have data over here, here, and here, and it doesn't matter where I read it, it's going to be the same across all of the different nodes. So that's consistency. Availability says the system continues to operate even in the presence of node failures. So you can have that node can fail. That node can fail over there. Oh, and that one failed over there too. Just in random node failures. That can happen all the time. That's availability, and your system is still running. Now, partition tolerance is like large chunks of your network can fail. yet even under that scenario, you can still have an operating cluster. Now, if we take a look here, we see strong consistency and availability. So you can remember, you only get 2 of the 3. So out of this, you get MySQL, SQL Server, MariaDB, probably Postgres. Those kinds of databases are in consistency and availability. Now you got consistency and partition tolerant with HBase, MongoDB, and Redis, where you can have large chunks of your network fail, but you still have a consistency across your cluster. And then availability is where you get availability and partition tolerance. This is the eventual consistency model. This is my favorite. I like these 2 at the bottom because it provides the best possible operations of a cluster that make it available pretty much forever. Like if you set it up properly, you'll have 100% uptime. You'll be able to provide availability and partition tolerance. Under the worst possible scenarios, you will still have enough distribution of server nodes that are able to communicate in a way that act to provide a very stable cluster. Now, what we're looking at when we're talking about RAFT, for example, RAFT is going to be more along the lines of being able, it does a pretty good job. However, it's stronger in the consistency section here, and it can have node failures and partition failures, but it struggles under some of the scenarios down here. So it's more close to the top on this side of the thing, I would say. Probably better up here. It's probably more like aligned up here. So if you're building RAFT, you're more in the SQL database server type of deals, and that's where that algorithm comes in.